Okay, so Candy, we've started this. I've just gone through some discussion with Crystal and Melissa about their schedules for next mod. So we're getting started on the class. Um, See it, let me know that you've watched this class after you've watched it, and I hope things went well at the doctor's. Anyway, we're going to start off with questions from Crystal and Melissa. Questions? Besides all of it?
Yeah.
Did you guys have a chance to look at that PowerPoint that I sent out over the weekend?
No, sorry. I did. And
Did it make sense?
it made sense, but then it didn't have anything to do with the, I don't know where I missed the y-axis. I mean, not y-axis, the, what was that question? I find the y-intercept. And then we were given these set of numbers. And I even have like, I got a grid and tried to, just to see if I understood it, and apparently I didn't. So,
Okay. Yeah. That was about regression analysis. Okay. Regression analysis is when you have data that is really scattered, that is not in a nice straight line, normal distribution, all this stuff. We call that a scatter plot, which is where you have points. We usually plot it on an XY axis. Remember that from your algebra classes. And the object is to look at these, and we're looking, a regression analysis is a way of creating a straight line that goes through the data and averages out the positions. And if you remember, the straight line equation was y equals mx plus b, where m was the slope of the line. In other words, how steep it was, positive or negative. Positive going up from left to right, negative going down from left to right. Okay. Irrelevant. I mean, as to the sign, because the slope is the slope, but we have a straight line, and b is where the line crosses the y-axis. In other words, where x equals 0. Okay, so what you have is, there's a couple of things. I was playing with Excel and could not make one of the functions give me any meaningful results. Good enough. But what I did look at was, how do you calculate slope? How do you calculate the y-intercept? Okay, and there is a function in Excel for calculating the intercept given an array of x and y data. And if you plug that in, and we'll see if we can pull that up and do some analysis on it. If you plug that in, it will give you the y-intercept. Or the slope rather. The slope of the line, positive or negative. If it's positive, you know it's going up from left to right. If it's negative, you know it's going down from left to right. We'll go through how you then draw that. You can also, there's a function called intercept. Using the same array of data will give you the y-intercept. Can you calculate these using the data? Yeah, but it's complicated. Excel gives us the tools. You can read and see what the basis is, just like you can look at a standard deviation and see the equation and go, oh my God, how am I going to do that? Excel does it, but the object is to look at the data and understand what it means. That's all. And so a regression analysis. So we also can calculate something called a correlation coefficient. Usually when we have data that is bivariable, meaning X and Y values or something like that, what we're doing is looking at two different sets of data to see if they are related. If they are correlated, it means that the behavior of each set of data is the same. In other words, if it is trending along like an up line, if you take a look at most graphs, and even though if it's squiggling around, if you look at stock market performance graphs, for instance, to use your last discussion, it might bounce around, but overall, over time, it's going up. That's called a trend. And the function trend is supposed to return the appropriate X values to be able to draw a line. I haven't been able to make it work. I don't know what I'm doing wrong. But that's okay. But the correlation coefficient tells us whether or not these things are correlated. Now, one thing that needs to be clearly understood is that just because two things behave the same way doesn't mean one causes the other. Favorite example comes out of this textbook, the Triola textbook. It talks about correlating the price of a slice of pizza in New York City with the price of a subway fare. And if you just look at those data, as the price of pizza goes up, the subway fare goes up. They're correlated. Or you can look at it the other way. As the price of subway fare goes up, the price of a slice of pizza goes up. I mean, and so the temptation is to say something silly like, you know, the price of pizza tells us what the price of subway fares are because it's causing the change. And that's obviously not true from a logical standpoint. But there are things that are causative. And causation is a totally different issue. And there, you know, we can correlate, for instance, certain behavioral aspects, such as drunken driving with automobile accidents. Now, automobile accidents happen whether people are drunk or not because they make stupid decisions in many cases. And, you know, the term accident, by the way, just means that it doesn't have to happen. It's preventable. But, you know, by whom? You know, maybe it's preventable by you, but if somebody just swerves into your car because they're changing lanes without looking, what the heck are you going to do about that other than have an insurance claim? You know, and hopefully nobody gets hurt. But we can correlate that. We can look at, for instance, the relationship between smoking and cancers and heart disease. We have seen that in large databases. So we can look at things that are cause and effect related, but things happen at the same time. I mean, we can, you know, and it turns out, of course, that if you really look at that New York example, slice of pizza, subway fares, it's really related to inflation. A totally outside factor that is there. Theoretically, I bet you could correlate those two things with the stock market change as well over time. And that's all about inflation, all about changes in the economy. So the issue with doing a correlation coefficient just says, are these two changing in the same way? If they're not, you know, so let's take I'm just going to draw here. Candy, I'm going to draw on the board. I know you can't see this. but I'm just going to draw a picture that's much like what is in assignment 3, which is a scatter plot of y and x that is following a trend. You can look at that and say, well, it sort of looks like everything's going up. You know, every x goes up with y and that sort of thing. You can look at that and say that. But showing it, calculating it is different. The formulas are complicated. I took a look at them and said, well, first off, if you can do it in Excel, why bother to memorize this stuff? The answer to that is not memorize it, but understand that it's a complicated calculation that has to be carried out. And it is something that in the days before we had statistical analytical software, and Excel isn't particularly good. For really sophisticated statistics, most people will use the software available from the SAS Institute, Statistical Analytical Services Institute, located in North Carolina. And virtually everyone in business will use SAS. But it's basically does the same thing, calculates all these parameters, whatever we need based on the data. Now, if we go to a different example, again, y, x, and those are our data points, there's no correlation. The coefficient of correlation is going to be very, very small. So there's no correlation between whatever those x and y values are. And that's really what we're looking at. So in the New York example of pizza and Subway fares, y would have been the price of a slice of pizza on a certain day, and x would have been the price of Subway fare on the same day. So we call that paired data because they are taken at the same time, so that we're really looking at that relationship. So if there is no relationship, the plot will just look like somebody sneezed on the graph, really literally, you know, as opposed to something that clearly is changing in some regular kind of fashion. Okay, so what we use when we're doing these correlations and we want to know the correlation coefficient in Excel, we will use Correl, C-O-R-R-E-L, for the correlation coefficient. We'll use, and if we want to have the line, all you're going to be asked for, I'll give you a little preview of the final exam. All you're going to be asked for on the final exam is the correlation coefficient, the slope, or the y-intercept. You will not be asked to draw a graph. Okay? Can you draw that graph? Absolutely, you can, just using the data. Okay, so we also have slope and we have intercept functions in Excel. And the slope will return the slope. Now remember, as I said before, I'm going to erase these plots for a moment. I think I've made the point with them. The equation for a straight line is y equals mx plus b. Now this is the same thing, I want you to remember, as b plus mx. Remember the commutative rule for addition. You can reverse it and it gives you the same answer. And in fact, the form b plus mx is what you will see in the final. Okay, so b is the y-intercept. And m is the slope. Remember, slope is defined as rise over run. And the way you do that, remember, rise is the y-axis, run is the x-axis. So if you look at two different points, okay, if you look at two different points, it is, so we've got point number 2 and point number 1. We number along the x-axis. So the one closest to the lowest value of x is number 1, and the higher value of x is number 2. Okay? So the value of y2 minus y1 over x2 minus x1, in other words, if we just draw this out as a right triangle, okay, this is going to be x2 minus x1, and this is going to be y2 minus y1.
So this is like coordinates on a map.
Exactly. It's coordinates on a map. Perfect example. Or, you know, just a laid out grid on graph paper,
Right.
if you're looking at this thing. So it's exactly the same thing. That's a good analogy. I like that. So having done that, what we can do, we know what B is, right? The y-intercept. So that's where x equals 0, okay? So x equals 0. Okay, if we draw out our graph, y, x, this is the 0 point. So the y-intercept is where your line crosses. Let's just draw it like that. Is where your line crosses the y-axis. Doesn't have to be below 0. It can be above 0, doesn't matter. We don't care about the x-intercept necessarily. All right? So what we can do is look at that. We know that we can calculate that x is 0, so we can then calculate a couple of other points. All we need to draw a straight line, you need 2 points, right? We have 1. The y-intercept is point number 1. Okay, so then we can say, okay, that's where x equals 0. We know m. So what is the value of y when x equals 3? Right? That makes sense?
No, because if I look at x equals 3, what is the value of y? So then I'm just looking at the point where
Y is 3.
yeah, like right there. So then,
Y is going to be 0, or whatever, you know, where
Oh,
if
that's Y.
maybe. We're not saying where y is 0. We can calculate where the x-intercept is. Okay.
so is that
By
why you
simply-
do y times 3 is 0 because 0 times 0 is 0?
No, not necessarily. Yeah, but what we know that y is 0. So remember the slope here, the equation here is y equals b plus mx. Okay, so we would set 0 equals b plus b plus m. 0 is going to be. Let's back off. I'm thinking too fast and trying to confuse myself. We know anytime you know two variables, or anytime you know one variable in an equation like this, and you have the constants, okay, we can calculate what the other has to be. Okay, so what we want is to know what the value of x is at y equals 0. Okay, so that means that we've got 0 equals mx plus b. So rearranging this algebraically, we're going to subtract b from both sides. And now we have minus b equals mx, or x is going to equal minus b over m. Okay? Make sense? Simple, straightforward. So we now have 2 points. We have a straight line. Plot the 2 points, draw the line, bingo. But we have to calculate the slope, which we do using Excel, because the calculation of a correlated set of data is complicated. Is this all making sense?
Kind of. I think once we put it into Excel, I think I might be able to understand a little bit more.
Yeah, we will do that. Actually, we'll do that in a little bit, okay? Because we're getting close to our, well, not that close. It's only 9:43. Okay, we got time. Let's pull up, and I'm gonna turn on the projector. Did that work?
I like some.
Okay. Yep, I hear that. So plug this thing in. Hope it works.
So if I'm opening Excel, would I do like a formula or would I do a blank workbook?
What I'd like to do is go to the worksheet from week 3. But you can do if you're putting in your own array of data, you just open up a blank workbook or go to a blank area of the screen. So let's do that. Let me see if I have. Let me see what I've got here. Right, that's the one I want. Now I want to do a new share. There. So Candy can see this. Okay, I've actually done these calculations. And here where you see this hashtag value, that's where I tried to do the trend and it didn't work. So these are the data that we have. You can see this, what we call a scatter plot. A scatter plot is just the data put onto a graph, right? So we've got the values of X, which is the horizontal axis, and Y, which is the vertical axis. And we see that they go up, you know, appropriately. This is the point that is X equal 37, Y equal 67. The nice thing about Excel is you put your cursor on that point and it tells you what those values are. So we're confirming that it's done. For instance, this value is 45 and 20. Remember, we always quote the X value first and the Y value second. Okay. So I've got the slope here that I calculated, but we'll go through that calculation and I'm going to put it in this particular box right here. So we go to more functions, which is where we find the statistical functions. And we go scroll down to slope. And the beauty of Excel, so these are the known values of Y, known Ys, okay, known values of Y. So we simply highlight those and plug it in. You can also plug in, just type in the range. And the known values of x give us that. And all we have to do then is say, is click on it. It's already calculated. If you look down here in this corner, here is the result. Okay, so that's okay. So we now know that the slope is 1.1, basically 1.5. Okay, so now we have m as 1.15. Okay, so now we want to know what the intercept is. Okay, and again, we want to do that. We go back to the, it's a little, to me, it's a little cumbersome to be going back and forth all the time on these things, but not much we can do about that. So we go down to intercept. This always means intercept, but it's a good point. Also, we can look at this particular description. Calculate the point at which a line will intersect the y-axis, blah, blah, blah. Okay, so again, we put in the known y's. And why they do this in reverse order, I don't know, but that's the way they do it. And the known x's. And again, we see the value here already calculated, plug it in. So we know that the y-intercept is minus 6.65. So it's going to be down around here, because this is a scale of 10. So we know that our line will have a value here of 1.15. So let's plug these in to our formula. And Candy, I'm sorry you can't see this, but I'll do my best to recite everything here. So we know here that our formula is going to be 0 equals mx plus b. We subtract b from both sides. We get minus b equals mx. Minus b over m is our x, is our value where y is 0. Okay? So we've got minus 6.65. And it's minus a minus 6.65, right? Because that's where the intercept is minus 6.65 over 1.15. So this becomes 6.65 over 1.15, which equals, and I'll pull out my handy dandy phone calculator. .65 divided by 1.15 is going to be 5.78. And this is then the x-intercept . So now we have 2 points. Pull out a ruler, draw your line. Okay, so we know, for instance, let's go over here to our plot.
So because of
Go
the
ahead.
negative outside of that negative.
Right.
the negative makes it a positive.
Yep.
Then
And we know from the look of this plot that the value at the x of the x-intercept is going to be positive, because all of the points that we have are to the positive side of the x-axis. If we had x points on the negative side, we'd know that that intercept was going to be negative. Okay, so here we have this, and this slope is positive, so the line is going up. So our 5.78 is pretty close to 6, so our x equals 0 point is right where I put the cursor here on this picture. Okay, right about here. Okay, I'm going to get rid of that. So our line then will go up through here. So we simply draw that, and that is our, what we call the best fit line. And basically what we've done is look at the slope, and we can go back through and calculate an x value, and this is what the trend analysis or the trend function should be doing. What it does is it goes back and looks at every y value and calculates an x, or every x value and calculates a y, so that we can actually have then a line that is a straight line here. But we don't need that if we're drawing this out. If we were putting this onto an Excel sheet, we would want to have all those, but it's fine. We can also calculate an x value for every y value. We have the y's. So if y is 4, okay, our first data point, they're telling us x is 10 on this plot. But if y is 4 and we plug that into our formula, we've got 4 equals minus 6.65 plus 1.5x. So we would have minus 2.65 over 1.15, which is going to be, it's going to be 2.15 rather, because it's minus 2.15, or 6.5, excuse me, 6.5 divided by 1.15 is going to be 2.3. So that's our x value, and that is lower than this, but it will be along the trend line. Notice that we've got our intercept is 5.78, where x is 0. So this will end up being probably actually right along in there. So we can calculate using the formula for each of these. It's a little more complicated than that, but nonetheless, we could use any value of y that we wanted. But what we want, but the value of using of calculating our straight line based on the slope and the y-intercept is that it actually is based on the best fit location. So using a different value of y isn't going to give us as accurate a number. We know two things. We know the slope, we know the y-intercept based on a full regression analysis done by Excel. Using those data, calculating the value of y at the, or the value of x, or the value of y where x is 0, allows us then to construct our straight line. So the value of y where x is 0, we calculated, or the value of x where y is 0, we calculate that point, then we have everything we need. Okay, so we can draw that. Now, it becomes a little more complicated to try and calculate an appropriate value for others. But the issue is that each point, and this is part of the problem with trying to do this by hand, each point has to be treated separately and compared, and there's a detailed calculation you go through for each of those. So the value of using Excel is they do all the hard work. But the issue is that the meaning of this is that there is, between these two, there is a correlation. Okay. Now let's take a look at the correlation coefficient. Correlation coefficient merely is a way of saying how closely aligned are these two data sets, X and Y. Okay. A high correlation coefficient would indicate that they're very closely related. Their behavior is very closely related. A low correlation coefficient indicates that they may be sort of related or they're, but not very much. And so let's again take a look at using now. I'm going to put down here, we'll do the correlation coefficient. I urge you when you're doing your final, you're going to have some of these questions. Pull up an Excel worksheet. You can even pull this one up so you remember what, so you remember how we did this. Pull up a worksheet, put in the data. The data sets are small, 5 or 6 points each one. So they're not like these with 15 data points. But the data sets are small. So here we want to do the correlation coefficient. Going back to statistical, go down here, you see Corel, which is not the name of a software company in this case, but Corel. So we look at returning the correlation coefficient between two data sets. So again, array 1, it doesn't matter which order you go in. Array 1, we'll call it the X's, and array 2, we'll call it the Y's. And again, we already see the value, so we say okay. We get a value that's carried out to a number of different, to a number of significant digits. In reality, it's 0.64. So what we're saying is that this is correlated. 0.64 means that the data are correlated. If it had been 0.15, we'd say, maybe not. What we want to do is all we're doing here is the interpretation is that these data are somewhat correlated. They follow the same analysis. Now, in assignment 3, the first question was to look at this stuff and use trend. If you can figure out how to use trend, teach me. I have not been able to make it work. But let's go over here and we'll see about trend analysis. So again, function, statistical, trend down here. And what this is supposed to do is return numbers in a linear trend known as data points using the least squares method. So let's, again, the Y's, the X's, and we're going to give an array here, which I'll go from here down to give those new values. And let's see what happens. See, they're not giving it to us. Okay. So I'm not sure what I'm leaving out. Let's try that again. I'm not, this is where I fault Excel, because if you'll notice in here, there is a logical reference. Okay. And what that means, I'm not sure. Let's look at help. I'm trying to help us all learn about this thing. Let's look at help. So blah, 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 naturally. The trend function. Input the formula in the top. No, we're not looking at the formula. In the toplet cell. Confirm the formula as a dynamic array formula. Otherwise, it must be entered as a legacy array. I'm not sure what that is. By first selecting the output and then input the formula in the top left cell of the output range. Confirm it. Okay. Not particularly helpful, is it? Known y's, known x's, new x's, a column for each independent variable. That have the same number. A logical value specifying whether you want to force the constant b to equal 0. If constant is true or omitted, b is calculated normally. If constant is false, b is set equal to 0, and the m values are adjusted so that y equals mx. So I think I was doing this correctly. So our known x's, our known y's, our new x values, for which you want to trend to return the corresponding y values. All right. Okay, I'm not sure how to make use of this. I'll experiment with this, and if I figure it out, I will let you know. However, you don't need it for your final exam, okay? All you really need is the correlation coefficient, and I think there's a couple of questions about intercept and slope. But these functions work. So when you're doing this, and again, your final, I've decided, given what's going on with this class and the fact that we've missed many classes, you're going to have 3 attempts at the final. Normally speaking, the final is one-shot deal. But I think here, I want you to learn. I want you to come out of this class understanding what we're doing. The kinds of questions that you'll be dealing with will unfortunately include something called z-scores, which we're going to go into after we take a short break. Recording. Okay. So I'm going to give you these 2 handouts. Candy, I will email them to you. One of them I'm going to have to scan, figure out how to scan it in here, but I'll get it to you. And this is another aspect that we've not had a chance to spend a lot of time on. So what I'm going to do is come back to that in a bit. But I'd like to talk about some of the other concepts that we've talked about. One of which is standard deviation and mean, median, and mode of data points. And what I'd like to do really is use these statistical functions. Remember that standard deviation for a sample is calculated by first calculating the squares of the sum of the squares of the differences between the data point and the mean. When calculating standard deviation, we don't care about our outliers. We're not worried about median. We always use the mean. So the mean, as you know, is calculated the standard way. Add everything up, divide by the number of data points. That gives you the mean. Each of those data points, then, we calculate the difference between the mean and the data point. It can be positive or negative. Okay, clearly, the mean is the middle of the data set. So calculating the positive and calculating the differences, if we just added those up, we'd get 0. Because half of them would be negative and half of them would be positive. That doesn't help us. So what we do for a standard deviation is actually take each of those, square each of those differences, square it, now it's a positive number, add those up. So we've got 15 data points, say in these arrays here. If we wanted to know what the standard deviation of the y values were, we calculate the mean, and then we'd add up 15 numbers that were taken by taking the difference between each data point and the mean and squaring it. So 15's not terrible, but if you had 1,500 data points, that's a lot of work. That's why we use computers. There is a standard deviation program. If we look at the statistical functions and go down to SDEV, we have 2 of them. Don't worry about SDEV A. Don't worry about that. That is that includes logical values like true, false, etc. And SDEV-PA is based on a population, again, using those logical values, yes and no, etc., true and false, that sort of thing. So we have a choice of the population standard deviation and the sample standard deviation. In every one of your calculations in this class, unless it specifies that it is a population, you will use the sample, okay? Because a population means everyone in that fits the criteria. If I live in Loveland, so if we wanted to do find out what the adult women thought about a certain topic, we would have a choice of surveying all women in Loveland, all adult women, and we'd specify what the age range was, but all the adult women, that would be a population if we could get every single woman in Loveland to do this. That's a lot of people because the population of Loveland is roughly 80,000. So theoretically, 40,000 of those are going to be female. That's not a given, but it's a good approximation. And some probably 25 to 30,000 of them would fit the definition of adult. That's an awful lot of people. But if we wanted to use the population data, then we'd use, if we wanted, we'd have to have them all. Otherwise, it's going to be a sample. And that sample, if we wanted to be meaningful, is at least going to be several hundred women.
So how did you put that grid in? You just copy and paste it in there, or?
What grid? What are you talking about?
So, like with last week's homework, this one, the X's and the Y's axis, you know how you have your grid in there.
Oh, yeah.
Did
Yeah.
you just copy and paste that in there, or?
That was, yeah, it was just put in
Okay.
to match the data. It is a scatter plot of the data. And let's see, what are the, let's take over here, look at the math. I think we can. No, those are, I can't remember how we do put in data, plots of data. I just don't remember that right now. Most recently used financial, logical, text, date and time, lookup and reference. I haven't done anything, done any data plots with Excel in so long, I'd have to look it up. But that was probably put in using the graph function, graphing function of Excel. No, formulas. I just don't remember. They changed Excel from when I learned to use it, and I haven't done that in a while. Yeah, probably both of us. But we use, it's probably put in a graphing function, and one of the graph types is this scatter plot, which only just puts in the data points, doesn't do anything with it.
Because I remember doing it in accounting.
Yeah.
Hall, but like you said, it's changed so much, and it's been a while since I used it, so I'm like, just don't remember how to do it.
Yeah, I'd have to go back and relearn all this. As I say, it's been a long time since I've done a lot of data analysis using Excel. Anyway, these functions here. So the statistical function of standard deviation for the sample. What the sample does then is take that sum that we have calculated, the squares of the differences between each data point and the mean, and add them up and divide it by one less than the number of data points. This is a long statistical explanation, but in terms of samples, we divide by one less than the number of data points. In a population, we divide by the number of data points. Now, what that gives us is actually what is called the variance. And the variance is a way of comparing the spread of data across different kinds of studies, different kinds of studies, how the studies compare in terms of that. We use that to calculate the coefficient of variance, which is another calculation. The coefficient of variance is simply we'll go into that in a bit. The coefficient of variance is something that we can easily calculate knowing the standard deviation and the mean. So the coefficient of variance is actually the standard deviation divided by the mean of the data set. And that can be, and at that point, but the first calculation, calculating that sum of the squares of the differences divided by 1, or divided by n minus 1 for the sample, is the variance. The square root of the variance is the standard deviation. So we do all that calculation and take the square root. Okay, one of the mistakes that people make when they do hand calculations of standard deviation is forget to take the square root. That gives you the variance, which is a valuable number, but it's not the standard deviation. Okay, so we calculate the standard deviation in that way. So let's just calculate the standard deviation of y. Okay, I'm going to just click over here in a box, bring up the function. And again, Excel is a great way to do it. It's easy to calculate a standard deviation if you've got a small data set like 4 or 5 numbers, or even half a dozen. It gets above that, use Excel. That's why we have it. So again, we highlight the values of y, and here we go. Our formula result is that the standard deviation is 17.12. Call it 17. That's the standard deviation. Standard deviations tell us a lot about the spread of the data. A larger standard deviation is a bigger spread. If you look at that document, I'm going to pull this up for Candy. And I'll be sending this, Candy, to you. And if we look at the variance in data in several things, we see that the higher the standard deviation, the more spread out things are. Hello, Cody. Howdy. In here for goodies?
For goodies.
Okay. Crystal, you want anything?
Spring cells. Pick up and run around.
Thank you.
You're welcome. Yeah. Yeah.
Thanks for lunch.
Yep. Have a good hour and a half.
So let's take a look at the coefficient, or at the standard deviation of the x's at this point. It ought to be pretty high, like the y's, because of course it's scattered across the plot as well. But let's do the x's, but it is much narrower in its range. And instead of going from a low of 4 to a high of 67, we're looking at a low of 10 to a high of about 45. So the standard deviation in that narrower range is 9.5. So it tells us, standard deviation tells us about where in the, how spread out the data are. There are standard deviations that can be as low as 2 or 3, or even one. In fact, one of the handouts that I'm giving um, uh, looks at um, at a normalized scale for comparing comparing data in different sets, comparing the variations in data in different sets. The normal, so these are, you'll be doing that on your final as well. But what I really want to get to is some other information here about, let's look again, look at another at another document that I have about standard deviation and variance, okay? So the, again, standard deviation is a measure of how spread out the numbers are. The symbol we use is the Greek letter sigma, small sigma, for samples. For populations, we use a capital sigma, but we're dealing with samples. Variance is the average of the squared differences from the mean. So all we do is look at the mean, calculate the mean, calculate the average difference, and this looks complicated, but if we do this in Excel, the variance turns out to be, to be calculated in that fashion. In this case, with these dog weight data, or height data rather, in millimeters, is being compared here. And the variance is a number here that's pretty high, 21,704. That means there's a lot of variation in our data set. If we look at each of them, we see that calculating each one's difference from the mean, which is just under 400, we find that we have some negative numbers and some positive numbers, but those are gotten rid of by squaring, so that we have this rather large number. And we divide by, in this particular case, we've got 5 animals. We're dividing by 5 because it's our entire group, our entire population. And then we take the square root of that to give us a number for the standard deviation. In a sample, we're going to be looking at n-1. Don't worry about this particular formula. It's the same thing as we were working with in class. 1 over n times the sum of the squares of the differences is the same as the sum of the squares of the differences divided by n, or n-1. So don't worry about this different expression. So let's.
Never understood why we have letters in math.
Letters are used to clearly define concepts. Sigma and every math, every different type of math uses its own terminology. So sigma in statistics always represents the standard deviation. We use general terms like X and Y and A and B to define as variables. But other numbers, other symbols, especially using Greek symbols, defines concepts. So, as I say, the symbol sigma always indicates a standard deviation in statistics. Okay. Capital P almost always denotes a probability. Okay, there are some other uses, but usually when we talk about P, it's a probability. Okay, so I'll probably forward this on to everyone, but it really, the standard deviation just means how spread out the numbers are, and the variance is a way of looking at the numbers is another way of looking at how spread out the data are. Okay, but the standard deviation is mainly what we use in most of our work and what we'll use here. You will calculate standard deviation for your final. Again, use Excel. Use those formulas. Let's see. Got this. Okay. Let's talk now. Let's go back to our go back to our text here and look at the concept of z-score. Let's just see, I think this is where we want to be. Measures, I think, of variation. And remember, our measures of variation include range, which is just the difference between the highest and lowest value, no matter what those values are in a data set. Our standard deviation, this is the formula. Let's back up one page here. This is the formula that we presented. Back up another page. The formula that we discussed here, standard deviation of a sample is the sum of the difference between the mean and our data point divided by the total number of data points less 1. So this is for a sample. Again, I tell you this is how we'll do it. The second formula is really the formula is the way that it's calculated in your computer program. If you carry out a set of calculations by hand, you will find that either of these formulas will give you the same result. So there's no difference between the results of these calculations. So to calculate our standard deviation, we compute the mean. We subtract the mean from each of those, subtract the mean from each sample. We're going to get a variety of numbers, positive and negative, square each of those, add them up, and then divide by n-1. That gives us the variance, which we then take the square root of to get the standard deviation. So this was going back to the chocolate chip data in the cookies. And they only looked at 4 values from one of the data sets to do this as an example. If you were doing this completely, you would use the entire data set. Okay. So there are 4 samples. If we look at this again, to calculate using the alternate formula, going through this complicated calculation, we get the same value. So it doesn't really matter, okay? So we have mean, range, standard deviation, and number. If we do this with the entire number of chocolate chips, we get a different standard deviation because there's a wider range than just the 4 values. I'm not going to go into the rule of thumb issue. I'll come back to why that's. So for a population, the standard deviation then is the mean of a population is denoted with the Greek letter mu because that tells us directly that it is a population we're dealing with. And then we divide by the total number, n, not n minus 1. The variance is equal to the square of the standard deviation. In other words, what we get before we take the square root. And it is basically a good general description of the amount that the data vary within the sample that we're dealing with. Dispersion and spread are sometimes used, but variance or instead of variation. The term variance has the definition of noting that it's an unbiased estimator. When we have samples, we have a biased data set because we haven't included everyone. The sample variance is actually what we call an unbiased estimate of the variation of the data. It's an unbiased estimator of the population. Remember, when we are looking at the population, we're looking at everyone. When we're looking at a sample, we're trying to make conclusions about the population based on that sample. And those conclusions have a certain amount of error. Okay. So we want to look at those. I'm not going to go into some of these others, but let's go here. I want to look at the variance, the normal of a normal distribution. Normal distribution is what we call a bell curve. Normal distribution of any parameter of a population is expected to be a bell curve. Normal distribution of a sample may not be a perfect bell curve. But when we are looking at the values here at data, we really, again, statistics has a purpose. The purpose is to draw conclusions. We can do all the analysis in the world, but presenting a bunch of numbers doesn't do anything. We're supposed to draw conclusions. We're supposed to infer information from that. That's called inferential statistics. Here we're looking at a normal distribution. As I've said many times, one standard deviation either side of the norm comprises 68% of the data. In other words, the standard deviation of 1 on either side will contain that in a normal distribution. 2 standard deviations comprise 95% of the data. So keeping that in mind, we have defined as looking at the likelihood of any random data point falling within 2 standard deviations of the mean is 95%. Just randomly choosing a data point. So you'd go in, let's just say we've looked at the height of high school freshmen. If we could survey every high school freshman in the country, we would come up with a standard, we would come up with a normal distribution. Obviously, that's very, very difficult. So what we generally do is use some form of sampling technique to get a broad cross-section of high school students, and with enough of them to provide us with a data set that will look approximately normal.
Now you're saying it's very, very difficult because the majority of them cannot be home or in class or.
It's difficult because it's an undertaking that requires a lot of effort. It's not particularly difficult in that we could go out and measure every high school student that was willing to participate. But accumulating that much data would be a massive and expensive effort. That's why we only do a decennial census in this country, because it is a massive effort. Fortunately, most people voluntarily participate. Those who don't return their census forms get a visit from a census taker who is on the job a federal official. So we have the right, I've done this, actually I did this one year just for fun. We have the right to go into people's property and talk to them. If they try to interfere with that right, it's federal crime.
So if they ever come to our house, we told them to go away, we're gonna answer their questions?
You can do that. And we will note that the field worker will note that the person refused to cooperate. In these cases, we have no authority to force cooperation. What happens then is we bump it up to a higher level within the Census Bureau, and then they do whatever they do to try and convince these people to cooperate. Ultimately, if we can't get them to cooperate, and you know, quite frankly, people have threatened census workers. They find themselves now being called on by the FBI or some other agency of law enforcement for threatening a federal official. Most people don't do that. But occasionally it happens. Most of the time when we go out, we find that they won't answer the door. We don't go walking around the house looking for them or any of that crap. We just, okay, we document that we're at the house at, say, 4:05 p.m. and rang the doorbell several times, knocked on the door, no one answered.
Nowadays, with all the scams and the criminals, I don't think I'd converse with somebody.
If someone claimed to be a census taker, you would ask for their identification. They have to have an ID, an official ID that says they work for the Census Bureau. Can that be faked? Probably, but we don't find that that's an issue. At least it hasn't been in the past. Yes, there are a lot of problems. That's why then we have the higher officials go and say, okay, here I am, here's my badge, I am an official with the Census Bureau, and we're trying to get these questions answered. They'll try and talk them into participating. But again, we cannot force such a thing. We cannot coerce, but we find that we can document that this many people refused and who it was. Okay? So that we have a record of that. We get very, very high compliance. When
I
I,
usually fill out my card, but
yeah, we usually do. I mean, it's just no big deal. But nonetheless, that's and it's, as I say, if we tried to do that with every high school freshman in the country, first off, we'd have to have enough people to get to all the high schools. We could try and get the data from the school nurses, but then they, for the most part, they don't know. If you don't go to the school nurse, they have no reason to even look at you, much less check your height. And of course, so this is just an example. So mainly it's going to be a population. But what this variance and what standard deviation and this normal curve and this statement that these things are within 1 or 2 standard deviations is if you randomly went and took another student's data, what would be the probability that they would fall within 2 standard deviations of the mean? And the answer is 95%. So and there is a 95% probability of that. So those falling outside that, more than 2 standard deviations away from the mean, would be considered unlikely results. Okay, so that's where the issue of likely versus unlikely comes in. Going out 3 standard deviations, we get 99.7% of the data. So anyone further out than 3 standard deviations is highly unlikely. So is it possible? Yes. Do we have these, string beans that have to duck to walk through a door? Yes, even in high school, even as freshmen. But they're very unusual. So what is a z-score? I gave you a handout, and Candy, I'm going to try and get you a copy of this somehow. That is that's a table of positive and negative z-scores. Z-scores are simply a measure of how far away from the center of your data set you are, the number of standard deviations. How do we calculate a z-score? We calculate a z-score by dividing the value of the data point by the standard deviation. So if our standard deviation is 2.6, which was the full cookie data set, the number of chocolate chips in Chips Ahoy regular, the standard deviation for the entire set that we had was 2.6. So if the mean was, say, 24, and your number was 22, then the difference between that data point and the mean is 2 minus 2. Since the mean is 24 and you had 22, subtract the mean from the data, from that data point, and you get minus 2. Your data, your standard deviation is 2.6. So we have 2 divided by 2.6. So it would be minus 0.76. That would be your z-score. That it means that you are basically 3/4 of the way toward 1 standard deviation. Does that make sense? So a z-score is simply a measure of how many standard deviations your data set, your data point is away from the mean. The z-score is a good way to compare different data sets. Also to compare without looking at the normal distribution and where your data point is in that normal distribution. That tells you that that 22 chip cookie is minus 0.76 a z-score, which means it is minus 0.76 deviations away from the center. So it is to the left, to the negative side of the normal distribution, and it tells you where on the normal distribution curve that data set or that data point lies. Does that make sense? Okay. Let's keep going here and talk about again, the coefficient of variation, something you're going to have to do in the final, is calculated simply by dividing the sample standard deviation by the mean of the sample. For a population, again, it's the same thing, dividing the standard deviation of the population by the mean of that population. So in terms of and that is basically a measure of how spread out the data is again. Okay. So again, to go back to the cookies, if our standard deviation was 2.6 and the mean of the population was 24, 2.6 divided by 24 would be a little over 0.1 or a little over 10%. So we express it usually as a percent, but it can be expressed as a decimal. Okay. So again, we've got, and the calculation is right down here. The coefficient of variation of the number of chocolate chips, the coefficient or the standard deviation was 2.6. The mean was 24. Multiply that by 100%, and so the coefficient of variation is 10.8%. Fairly straightforward. We won't look at, we haven't talked about the weights of Coke cans, but at least not too much. So so there is there is another thing you will be doing on the final is calculating this coefficient of variation. So since your final is, you're just gonna do that, we can get started on it in class if we have time on Wednesday, but it would be available online to get done before the end of the weekend as well. You do have 3 tries, so take your time when you're working on it. Look these things up if you don't remember them. See how to calculate them. Now, what I don't know, let's go back to this spreadsheet. Here we are. What I don't know, quite frankly, is if we can calculate the coefficient of variation Okay, that's covariances. We don't care about that. We can calculate the variance. I don't see where we have that, but that's okay. We calculated here the standard deviation of the values of X, and we calculated the standard deviations of the calculated values of Y. So if we wanted to know what the coefficient of variation was between these two, we would calculate the mean. So let's calculate the mean of Y. And again, this is the average. Remember that Excel uses average instead of mean. It's the arithmetic mean. So we have the average and we want to do Y. And we find that the average value of Y, the mean of Y, is 24.533. Note that, that is over a range of 63. So that's an average value. So if we want to do the mean or the average of X, let's just take a look at that as well. And the average of X is 27, okay? Note that the standard deviation is lower in X than it is in Y. So I'm going to calculate now the coefficient of variation of Y. And I'm going to do that using standard formulas. And that's going to be, remember, equal. And we're going to divide the standard deviation. So that's going to be H22. I'm going to divide that by the mean, which is H23. And then enter it. So our coefficient of variation for the X is 0.34. So let's do the same thing for the Y's. And that's going to be equals H20. That's the standard deviation divided by H21. Enter that and we get 0.69. So what we're seeing, again, by comparing these coefficient of variations, we have another indicator of how spread out the data are. So the coefficient of variation here tells us something we already know just from looking at the range. The range of Y is 4 to 67 or 63. The range of X is 10 to 45 or 35. So the range is much smaller for X than Y. We expect the coefficient of variation to be much smaller for X than Y. And indeed it is 0.35 versus 0.7. Make sense? So we have lots of ways of looking at our data and confirming it. So, and they all have different values in statistical analysis, and we're not going to be able to cover all of those different things. But nonetheless, we can calculate these things, and you'll be seeing coefficient of variation. So remember, that's simply the standard deviation divided by the mean. Okay? And we can actually set this up as a formula, but you're going to have to calculate both standard deviation and mean to get them. Okay? So that's how you do that. Standard deviation, use the standard SDEV, generally speaking, SDEV S for sample, unless you were told that you are sampling the entire, you are surveying or getting data from the entire population, in which case you'd use SDEV-P. There are differences in the calculation. Because you're dividing by a different denominator. So if you were to do population instead of sample, you would get a lower mean because you're dividing by a higher number. The first part of the calculation is exactly the same. The difference between the squares of the differences between each data point and the mean, the sum of those squares. So that's going to be the same. So you're going to get different values. So it's important that you use the right formula. And one of the things I will make certain of is that indeed you have the right formula. Okay. Questions? Okay, so let's go back to here and go back to looking at the weeks. Okay, I wanted to save that. Okay, so, yep, I'm going to save it. I changed some of the wording on the questions to make them more truthful. Okay, let's go look at, let's go back here to the modules and we'll look at this week. The discussion this week is about correlation and causality. Remember we talked about that briefly. And you're going to look up something in your career field, and you'll have to do some searching to come up with causation versus correlation. We see it, I mentioned a couple of things in medicine already that we see, so you may want to look at that as well. I recommend this Khan Academy video. It actually is pretty good. Most of the Khan Academy stuff is pretty good. Some of it gets a little cheesy at times, but you have to remember they're really aiming it at a very, very broad audience. So that'll be this week's discussion. And the in-class activity, since we're not here to do this, we'll see what we can do on Wednesday, and if you and I might do something for you when we get to the next half of the class. We're about to come to the end of what we're doing here. Looking at the only other thing this week, obviously, is the final. So what I want everyone to do is get caught up. But let's back up and look at last week. The assignment last week was regression. Let's see about week 3. We read only. Let's bring that up. We looked at the data for week 3. So what we're looking here at the raw data for week 3, you're going to find the slope and y-intercept. Don't worry about the use that information to tell us what the equation of that best fit line is. And again, if you can figure out how to use trend, tell me. I haven't been able to make it work, and their explanation is not clear to me. Think about how this might think about how this might fit into your career. I'm not going to be real hot on that particular one. Probability. Let's talk about probability. Probability is the chance of something happening. That's all. When we roll a single die, there is a 1/6 possibility of it coming up a 1, because there's 6 sides and they're random. So you have a 1/6 or 16.67% chance of getting a 1. Every single time you roll the dice, that probability is the same. So the chances are 5 out of 6 that when you roll it again, it'll be something else beside a 1. There is also a 1 in 6 chance that it will be a 1 again. The way we take these multiple trials to calculate the probability of the same result is to multiply the probabilities of that result. So you have a 1 in 6 chance of getting a 1 the first time. If you do, you have a 1 in 6 chance of getting a 1 the second time. If you do, that means it's a 1/6 times 1/6 or 1/36 probability. 36 divided into 1 is a little under 3. So there's less than a 3% chance, which if we go back to that normal distribution is outside that 95% of being within 2 standard deviations. So it's an unlikely event. Does that make sense? Okay, very, very much an unlikely event. Okay, so anyway, if we go here, you know, okay, there's that's related to part of number 3, but again, we take a look at the likelihood, predicting genders randomly of somebody coming in without knowing any other information about them. There's 2 genders. So you have a 50-50 chance of guessing the right one. And again, we express this as a percentage. So a 50% chance is a 50% probability. Okay, if someone says, well, there's a 1 in 5 chance that I will, that I'll find a quarter on my way into school today, because based on experience that 1 in every 5 times he finds a quarter. It's kind of a silly example, but that means there is a 1/5 or 0.2 or 20% chance. Now that means that it's 20% today, 20% tomorrow, 20% the next day, and it can keep going, every time. So, and there is a possibility that he might go 10 times without finding that quarter. What's the probability of that? Well, there is an 80% probability. We have this thing called a complement, which often is written as, the probability of an event is written as capital P parenthesis, name the event. We'll call it Q for quarter in this case. The probability of finding that quarter is 20%. The probability of not finding that quarter then is the difference between 100% and 20% or 80%. Each day, there is an 80% probability he won't find his quarter. That's called the complement. The complement of the probability of an event happening is the probability of the event not happening.
Really wouldn't call it a compliment though. I mean, because you're only picking it up 20%, so the 80% you're not picking it up. It's not really a compliment.
Well, complement is a mathematical term meaning the other side of, not to pun, the other side of the coin, right? The other side of the event occurring is it not occurring. So the complement is simply the difference between 100% and 80% in this case, or since the probability can be expressed as a decimal, 0.2, the difference between 1 and 0.2, which is 0.8. So again, the probability of not finding that coin is 80% every single time he does. So the chance of finding that coin being 20%. So what's the probability of finding 2 in a row? Well, 20% times 20% is 0.2 times 0.2, 0.04, less than 5%. So it's unlikely that 2 days in a row he's going to do that. But probabilities are such that anything can happen. You know, he might go 5 days in a row finding quarters. The probability of that, very small. The thing about probabilities is we calculate the likelihood of something happening. What we're saying is that it could happen. It's just not very likely or very unlikely in the case of this example. So we can find that. Let's take a look down further in this assignment. A survey taken at a K to 6th grade school. Do you have enough time at lunch? So what we are looking at as the boys and girls were asked. The girls said there were 153 or 52 girls, because we have a total here of respondents of 42 yeses and 110 nos. So there's 152 girls. We have boys. There's 148 boys, 95 of which say they have plenty of time at lunch, and 53 say they don't. Okay? That may be a reflection that boys eat faster than girls. Who knows? It could also be some negative that we won't go into about the girls. But if what we're looking at is, so there's a total of 152 plus 148, or 300 boys and girls. So the probability of randomly selecting a response that came from a boy is going to be 148 out of 300. So we divide that and calculate a percentage, right? So let's look at that and do that. So there's 148 boys divided by 300 students. So the probability is 49.33%, or 0.493, that a randomly chosen response will come from a boy. The complement is denoted as we note here, P of B with a line over the top. That means the complement of P of B, the probability of it being a boy. So the complement is going to be the difference there, or 50.7 or 50.67%. That 1 minus 100% minus the probability of the boys, right? If the probability of the response being a boy is 0.4933, then 1 minus 0.4933 is 0.5067, or 50.67%. Remember, the complement of a probability is the difference between that and 100%.
When I did that, I got negative 3.9.
Okay, how did you do that?
So, or set times.
No. No. To find the complement, it's the difference between 1 and 0.4933. Remember, the complement of a probability is the difference between that probability and 100%. So if the probability of a boy is 0.4933, 1 minus 0.4933 is the probability of it not being a boy, which is another way of saying the probability of being a girl. That makes sense?
Kind of.
Okay. Remember the definition of complement. As a matter of fact, you weren't here the other day, and I have some definitions for you. These are the chapter 4 definitions that we're using. You're welcome. I could not get it scanned in, so. So there you have that, and Candy and Melissa have it as well. So we're looking at these data. So the probability, and we can look at the data from all sorts of different viewpoints. We can total up the number of girls. We did. It was 152. Total up the number of boys, 148. The total number of yes responses was 137. That's 42 plus 95. The total number of no responses was 163. So we can, now that we know those, we know that the total number of responses was 300. The probability that the selected answer was no is simply the total number of no responses divided by 300. And again, if this is just randomly selecting in an unbiased way one of the responses.
So it would be the total of number, which is 300.
Right.
Divided by 163.
No, 163 divided by 300. Probability is always going to be 1 or less, with a probability of 1 being 100%, meaning something is going to happen, period. It can be all the way down to 0 to the chance that nothing, that it will not happen. You know, and an example of something that would not happen is you roll a die and it lands on a flat surface. It lands standing on a point. That never can happen. So that would be a probability of 0. Rolling a die and it will come up with a number between 1 and 6. That's true. That's 100%. It will come up with one of those numbers. So probabilities are always between 0 and 1, or 0% and 100%. So if you're calculating a probability and you get a number above 100%, you just probably inverted the calculation. You know, anytime you see anybody say, I'm going to give 110%, that's garbage. You can't give more than 100%. That's all we got. You know, so keep that in mind. So you can calculate those probabilities. Factorial. Let's go down here and look at factorial. You remember what factorial is from my talk the other day? Okay, a factorial is a mathematical concept where you take the number, if you like 5 factorial would be 5 times 4 times 3 times 2 times 1. And that's going to add up to, I think, 120. So what we use factorials for is when we are taking a group of items and saying, how many ways can we arrange this?
Why would you want to see how many ways there could arrange it? Like, why make, I'm not trying to be lazy here, but why make more work for yourself?
This goes into calculations like permutations and combinations. It's the sort of thing that we use in calculating, for instance, the number of license plates that we can issue given a structure like 3 letters, 3 numbers. How many ways can we combine 3 numbers or 3 letters? Okay, we've got 26 letters. How many ways can we combine those in 3-letter combinations, including repeats of each letter? It's a lot. So it's a way of calculating, and factorials come in very useful in that, because the calculations, like in the video that or the video of class on last Wednesday, we were talking about combinations. Many of these things involve dividing one factorial number by another. Well, the calculation is much easier if you've got a factorial number. One of them is a higher number than the other. You can simply take out everything below. Let's just see, we've got.
But then that just starts becoming into people's opinions.
No. I mean, these are fairly objective numbers. How many ways can we combine these things? Right?
Right.
So if you've got, and this is something important, from a standpoint of, say, the motor vehicles department, how many license plate numbers can you have? It gets pretty large when you think about it, because we've got 26 letters and 10, well, actually 9, because we can have zeros, 10 numbers, 1 to 10, or 0 to 10, right? Or 0 to 9, right? So we got 10 numbers. We can combine those in a lot of ways. Now it becomes more complicated. We're going to assume now that we can't have combinations involving multiple iterations of the numbers. Okay? So we've got 26 letters. If we've only got 3 of them, then we've got 26 possible letters, but we have to reduce this by the number we've taken out. We can only use 3 at a time. So our first letter, we have 26 choices. Our second letter, we have 25 choices. Our third letter, we have 23 choices. Okay? But we've got 26 to choose from. So we have 26 minus 3, which is the number we can have. Okay, this is the formula we have. And this is also factorial. So we've got 26 factorial over 23 factorial. Well, if we try to plug those into our calculator, we're going to get enormous numbers. So let's look at this. If a factorial is 26 times 25 times 24 times 23 times all the way down to 1, okay? This portion is the same as 23 factorial, because it's 23 times 22 times 21, etc. Divided by 23 factorial. These cancel. So now our number is 26 times 25 times 24, which is easily handled with a calculator. And that tells us how many of those we can have. our 10 numbers do it the same way. 10 factorial divided by 10 minus 3 factorial becomes 10 factorial over 7 factorial. And this becomes 10 times 9 times 8 times 7 factorial over 7 factorial. So we've got 10 times 9 times 8. Much easier numbers to deal with. And the factorials help us really do the math a lot faster, but understand that we are taking out lots and lots of potentials. If we could have a license plate with 26 letters on it, we'd have more license plates than the population of the earth. The way we're going in this country, we might need those with all the cars and trucks and everything else we have. But nonetheless, factorial is simply a notation for take your number and then multiply it by it minus 1, minus 2, et cetera, all the way down to 1. Never get to 0, because 0 times anything is 0, right? So that's what factorial is. So as I say, 5 factorial is 5 times 4 times 3 times 2 times 1. 100 factorial is 100 times 99 times 98 times 97. And it goes on like that 100 bottles of beer on the wall song, right? But all the way down. And it gets to be a pretty enormous number after a very short while. 6 factorial is, 5 factorial is 120. 6 factorial is 720. 7 factorial is going to be way over 42,000. Adds up in a hurry, doesn't it? Yeah, adds up in a hurry. But they're very useful constructs for certain kinds of calculations. And it, as I say, it makes things much easier mathematically if you're doing it by hand with these kinds of calculations. Again, you plug it into a computer, you know, it's going to do things a different way. But the fact is we can get rid of much of the what looks like heavy calculation by simply recognizing that we can kick out a lot of the information. So you'll be calculating factorials, okay? Now let's look at these permutations and combinations. They're on the homework. I don't believe you're going to see any of those in the final. I haven't decided if I'm going to add a question or not. I just haven't made a decision on that. Okay, so we have, if you're allowed to use if you have numbers 1 to 9 and have to choose a passcode that's 4 digits, how many possibilities are there? Well, we've got 1 to 9. Let's just take a quick look here. We've got 1 to 9, which is 9 possibilities. Nine possibilities and 4 choices. So we've got 9 factorial possibilities, right? We've got 9 minus 4 because we're only able to use 4. Okay, so we subtract those out. Again, our first digit is 9. We have 9 choices. Our second digit, there's 8 left. We have 8 choices. Our third digit, we have 7 choices. Our fourth digit, we have 6 choices.
So
because we take them out.
9 factorial over 6 factorial?
No, over 5 factorial, because we've taken
Oh,
out
sorry,
4, right?
five
Yeah,
factorial.
exactly, yeah. You got it. 9 factorial over 5 factorial, which is going to be 9 times 8 times 7 times 6. Because then we have times 5 factorial divided by 5 factorial. Those cancel out, so that's how many choices for our passcode. Whatever that calculates out to be, 72 times 7 times 6, 72 times 42. So we have a lot of choices, right? That's why guessing a passcode is not easy if you don't have any other clue as to what someone may choose. Or if you are setting these things up, it's just like, garage door openers. They have all those little pins. There's like 12 pins or so. So you've got 12 different settings. Actually, you've got more than that because you can have 3 settings for each pin. Okay, you've got a lot of choices, a lot of combinations that you can put together. But it's finite. It can be calculated. And by some bizarre coincidence, at our house in Arvada, turned out one of our neighbors reset his combination to one of ours. And so we're sitting there one day, and all of a sudden our garage door opens. How'd this happen? So we closed it. Who knows? Somebody, who knows? Maybe a big heavy insect ran into the button. Who knows? It happened again. So I changed my combination.
So was he opening his door and yours was going up as well?
Yep.
Oh.
And my neighbors were pretty good folks. I don't think I had thieves for neighbors, but
Yeah,
not good.
no,
Because of course that meant that I could open his.
right.
So, got changed. So we can do that. There is, so look at this. The permutations and combinations are in your textbook. Take a look at those. And what we have is a slight difference. And that here, permutations are what we've just calculated. This is a number of ways you can arrange things. In this case, the order doesn't matter. And in fact, you can use these kinds of calculations for each of these examples, each of these questions. Combinations are different in that permutations, you don't care about the order. So 1, 2, 3, 4 is the same as 4, 3, 2, 1, or is different than 4, 3, 2, 1, even though they're the same 4 numbers. In combinations, order does matter. So 1, 2, 3, 4 is the same as 4, 3, 2, 1. You've grouped all 4 of those numbers together. Okay. So fortunately, with things like keypads, the order does matter because indeed 1, 2, 3, 4 is different than 4, 3, 2, 1. But in other situations, that might not be the case. So I don't think you have to worry about that here. But it is something to be aware of. There's 2 ways of looking at these things. For the most part, we're just interested in how we can arrange things. The other thing is that when we are looking at permutations, it depends on how we want to define it. If we have our class our freshman English class in high school, and we wanted to have the students line up. We can do it by alphabetical order, which would not be a permutation. It would be an order. So we would have a fixed order. We could do it by height. Same thing, a fixed order. But if it were random, it didn't matter gender, height, name, anything, we'd have, if we had a class of 30, we would have 30 factorial ways of arranging these students. Okay, so that's why we have this. I mean, and that's one of the reasons that when we are in school, when we want things done in some specific order, it's going to be usually alphabetical. Doesn't have to be. There's no reason other than convenience that a roster of students has to be alphabetical. It's just convenient. It's easy to sort. There's no reason that we can't arrange things by height. No reason we can't arrange things by birthday. And remember, statistically, a birthday in that respect is just a label. Okay, so does that make sense?
Mhm.
Okay, so that's really where we are with this, with week 3 assignment. So at this point, it's a good time for us to go off to Power Hour and let you get started. Candy, when you watch this, just let me know that you've done so. The code word for this one is London, London. So I will look forward to an email from you. I hope things have gone well. And if you have questions, of course, let me know. And Wednesday we'll be prepared for finishing out the class. So I'm going to stop the recording and then close the meeting.